Okay, so here's the what we had from class. Okay, so if you weren't in class, I know somebody was absent. You can kind of look at the code and stop the video and type in the lines of code for yourself. And so I'll just slowly scroll it just for those purposes. Here's another block. You could pause, type in the initialized vectors, and we didn't complete the code with the displays and pods. So that's what we're going to be trying to do in the next few minutes, is figuring out how to finish this up. Okay, so you can see we had a problem where we have a braking force of negative 2,000 newtons. We had an initial velocity of 30. We have a mass for our vehicle of 1,500 kilograms. We're going to look at this over 5 seconds, and we're taking small time steps, 1/10 of a second. Now, actually, for the computer, that's not that small. We could easily make those steps much smaller, but more smaller time steps will give us more precise results, right? So using that, notice this is a constant force problem. So when we get down to the calculations, we'll see we get a constant acceleration. All right. So we had the initializing of vectors. This gives us our time. This line here, 15, gives us the length of the time. Then we created vectors for v and x. So we have storage space, but like in the previous videos, those are full of zeros right now. I liken this to a bookshelf that doesn't have any books on it yet. We've created the shelf so that we will be able to put information on it, but the information isn't there yet. It's all zeroed out. But it's always good to have space to store things before you start unloading the books, so to speak. So it tells us how much shelving we'll have before we go into creating the things that will go onto the shelves. All right. So then we get to the calculation section. Since f is constant, this is a simple case where we can get a single value of a because it stays the same throughout the problem by using Newton's second law. All right. Then, before we go into the loop to compute all of the velocities and positions, we need to set their starting values, right? Because we can't step from a value if we don't know what the value is, all right? So then we get down to our loop. And remember, in the previous video, I said we had an error in this loop. We can't go from 1 all the way to nt because it plus 1, we have to have room for that last it plus 1, okay? So we can't go beyond nt, and since we're going to add 1 here, we have to subtract 1 from nt. So it turns out our time vector is 51 units long. If we go from 1 to 51, we'll end up trying to calculate the velocity for the 52nd step, and it doesn't exist. So we'll get an error for that. So by bringing this down to nt minus 1, there will be 50 steps, and that will take us to the 51st velocity at the end of this. So this is a little formula for time stepping the velocity. We take our velocity at the beginning of the time intervals of the time step. We add our acceleration times the length of time to it. So this is just like v final equals v naught plus at. We get the next velocity from the velocity where we are and adding a little acceleration times time. So we're accelerating for a little bit of time to add on to the velocity we already had. Then we do the same thing to get the next position. We use the position where we are, and we look at how fast we're going, and we apply that speed for the time step to give us a little more distance and add that on to where we already were. Okay. At this point, we're ready to create some graphs, all right? And we're going to also talk about retrieving values like we did in the previous video, all right? So if I wanted to just know what the last time is, I can use DISP. So this is just a display, okay? And let me do, if I want the last one, I know there are NT times, so I can do V of and whoops, it was a capital N, and it's a lowercase v, v of nt. And I believe this will display the last velocity. So let's run the program and see if it works. Okay, so it just gives us the number 23.333. Okay, so it looks like we'll be going 23.3 roughly meters per second. Now you might remember we can make this a little bit nicer by saying something like we can concatenate a string. So if I put a bracket there, I can start by putting in a string final velocity equals end that string, comma, okay, and then I want to put in the velocity. Now the problem is right now velocity is being stored as a number, right? And if you're trying to print a string, you need to num to string that velocity value. So let me put one more parentheses in. And so it will convert the number 23.333 basically into a word. It'll treat it like a word now, okay? And so if I run it with that display command, it will tell me that the velocity, you know, it puts a little bit of text with that, all right? It might be nice to have an extra space after the equal sign. So if I run that again, it'll be spaced a little more nicely. If I wanted units on that, I could keep concatenating the string and add the text meters per second between apostrophes. Okay, those are, sort of think of those as quotation marks. Okay, so single quote mark. And so that adds another string of meters per second onto the string. So final velocity equals is one string. We created a string of the velocity number, and then we made meters per second a string. And if I display that, I have units tacked on. If I want a space in the units, I'll put a space inside of that last string because it just sticks those all together. Likewise, I could display the final position. Do basically identical things here, and num to string. And then I could have, let's see, final position would be x of nt. Okay, and so then I want to close that. I need one more parentheses, comma, and then I want to do that in meters. And square bracket. The square brackets tell me that I'm sticking several strings together. That's what allows me to do that. And so down in the command window, it now tells me what the final position will be, okay, based on what I have here, okay? So that's displaying the values. But now let's say I wanted to find what the speed was at 2 seconds, okay? I could use the command, let's let T2, because this will be the time at 2 seconds. Let me just do the find command. Find T equals, actually I have to put a double equal sign. I didn't do that correctly in the last video. I'm not doing an assignment. I'm saying equals. And I want to find where the T vector is equal to 2. And let's see, it did not return a value. Let me just pause the video for a moment and figure out what it is that I need to do. That was easy enough. I had put a semicolon after the find T equals 2. And whenever you have a semicolon, it doesn't print in the command window. So I didn't want the semicolon at the end of find where T is equal to 2. And it tells me that that would be the 21st time step. So now I can say V, I can write V of 21. And that tells me how fast I'm going at 2 seconds. X of 21, that would be the 21st X value in the string of 51 X values. That would happen at 2 seconds as well. So that would be 57.4667 meters. All right. Now the last thing I want to do is show how to plot. Okay. But we want to probably plot the X and Y, I'm sorry, the velocity data, and we want to be able to plot the position data. So let's come up with another parameter called plot choice. We're going to set it equal to 1 first. And let's say that 1 equals position time, and 2 equals velocity time. So we can now come down below here under our displays, and we can create some switch case statements. We're going to switch on plot choice. And then let's type in case 1, and I'll put a comment, that's position time. And we have a space case 2, velocity time. And those are all of the cases, so we'll end it, and so we have a skeleton of our switch case statements, right? So if I want to plot position time, I'm just going to do a static graph. All I have to do is plot t comma x. That will pair up, as we talked about in the last video, all of the t values with all of the x values and give me 51 points to plot. I can do the same thing down here. I can plot t comma v, and that would pair up all of the time and velocity values to plot if I have case 2. Now let me run this program. It's in plot choice 1, so it should be position time. And down in the command window, it did give me the final positions, but I should be seeing a figure pop up, and there we have it. Okay, so our position time graph looks like what we have here, okay? So we're slowing down, but not all that rapidly. So that is a curved graph. Let me dock the figure. The way you dock it is you use the little arrow in the corner that's there, and I can dock it into where the workspace is. And I have a curved graph here. If I want to see more curvature, I could make the braking force bigger. Okay, so let's make the braking force 4,000, run it again. And you can see a little more curvature to that because we're braking harder. Okay, the car is going to slow more because of this. And so we have, that is a parabolic curve. It's not so obvious looking at it that it's parabolic, but that's what's happening there. Okay, so that gives me the plot of position versus time. If I, in my parameters, switch to plot choice 2, and let me actually add a space for initializing vectors. I switch to plot choice 2, I have my velocity time graph. And that's going down in a linear fashion because we have a constant deceleration, right? Now, right now, these graphs aren't very interesting because they don't have titles and axes. So let me just do this for the first graph, title. We can put a string on there. Position time, okay, will be the title of this graph. I need to go back to plot choice 1 if I want to see that. Okay, so I'm in plot choice 1, and if I run it, I see the title position time. You might want to turn, do some labels. Let's do an X label. X label would be time in seconds. And Y label would be position in meters. So now if I run this, we have X and Y labels. There's some nice little things you can do, like, let's see, we could put in a grid. We could put grid on, If you see, if I run that, you can now see there's a grid in the graph. If you want it to be a finer grid, you can do grid minor. And that puts finer markings within the grid. So all of those things are nice things you can do and add them to your plot to make it, the graph look better. You obviously want a title and labels, and the grid lines are often nice. And you could do the same thing to the velocity time graph to finish that up. So when you finish this video, you should have been coding along and making all of the changes that I made to the code that we had in class. So I'll scroll it slowly in little steps. So if you need to pause the video and make sure you have your code up to date, we'll be using it again in class, so you want yours to be up to date. You can copy everything that I have here.